ABot-World-0, Infinite Interactive World Rollout on a single desktop GPU by the ABot-World team, July 2026. You handed us this paper, and it's frankly the single biggest engineering flex of the year.
Oh, absolutely. It's a total paradigm shift.
Right. So our mission for you on this episode of AI Paper Slop is to figure out exactly how they took a consumer-grade NVIDIA RTX 5090 and essentially crammed an infinite 720p interactive world simulator into it.
Yeah, and doing it in real time.
Exactly. We're talking 16 frames per second with just a 1.2 second action to first frame latency. And spoiler alert, they did not pull this off by just, blindly throwing more compute at a video model.
No, not at all. I mean, to put this into perspective for anyone who's currently trying to scale generative simulation, the team solved the closed-loop generation problem across 3 completely distinct pillars.
Like they rebuild the whole stack.
Exactly. First, they built this active closed-loop data engine called World Explorer. Then, they built a bidirectional-to-causal training pipeline using this wild new technique called LongForcing.
Which is just brilliant.
Yeah, it completely eliminates autoregressive drift. And finally, they did this absolute masterclass in full-stack inference co-design. So, mixed precision, a super lightweight VAE, and bounded KV caching.
I was actually reading through this paper, and I kept looking for the brute force scaling law. Like, where's the massive cluster of H100s doing the heavy lifting? But it's not there.
Right, because they realized interactive world modeling is fundamentally a systems challenge.
Yeah. So to understand how this goes way beyond just generating pretty video clips, we really have to start at the foundation. I mean, if you're building a persistent world, scaling a video model isn't enough. You need temporally coherent data, right?
Yeah, temporally coherent data with really reliable action supervision.
Exactly. And the way ABot-World-0 approaches this just completely shatters the standard scrape and train paradigm.
Well, the data bottleneck for interactive worlds is incredibly strict. I mean, that's why standard scraping just fails outright.
Right, because if you just grab passive internet video, you get all this visual diversity.
But no synchronized control input.
Exactly. Yeah. And if you use game recordings, sure, you get the exact keyboard inputs. But the data is stylistically so narrow.
And then if you use pure simulations, you get perfect geometry, but you're stuck manually designing every single trajectory.
Which doesn't scale at all.
Yeah.
So the team's big insight was to stop treating these as mutually exclusive. They built this multi-source infrastructure.
Yeah. 3 distinct sources. So first you have AAA games, which give you those ground truth API control signals, perfectly synchronized keyboard and mouse inputs.
Right.
Second, you have simulation data from Unreal Engine and 3D Gaussian splatting. But they aren't just using generic game assets here.
No, they're pulling in proprietary street aerials, right?
Exactly. Street scanning data reconstructed via their ABot 3DGS pipeline. So they get these photorealistic, real-world scenes with absolutely perfect geometric precision.
And then finally, the third source, they integrate internet videos to inject massive domain diversity.
Merging those 3 is just a monumental task. I mean, they had to create a unified action representation.
So that the observer-style roaming from the simulation data and the actor-style motion from the game data all map to the exact same discrete keyboard action space.
Exactly.
But wait, I want to push back on that third data source for a second, because this is where the paper really made me stop and think.
The internet video.
Yeah. Because if you have internet video that is totally passive, like just raw MP4s scraped from the web of someone walking down a street or driving a car, how on earth are they extracting action labels from that?
Right, because there's no keyboard attached to a YouTube vlog.
Exactly. You're training an action condition model, but there are no actions.
So they engineered this highly robust pose estimation and segmentation pipeline to extract what they call pseudo-labels.
Okay, break that down for us.
So they take the raw internet data and they run it through tools like ColMap and VAE. ColMap is a structure from motion tool.
Right. It recovers camera trajectories.
Exactly. The 6 degrees of freedom camera trajectories from the raw video. And then VAE helps analyze the pose and depth.
Oh, wow. So once they have those frame-to-frame translational and rotational displacements,
right, the exact camera movement,
they mathematically project those continuous movements onto the camera basis vectors.
Yep. And once they have those projections, they threshold the continuous physical movements into discrete buckets.
And those buckets match the WASD keyboard action space from the game and sim data.
Exactly. So a forward translational displacement mathematically becomes a W key press.
That is so clever.
It is. I mean, obviously, it inherently carries some estimation noise compared to the clean API data from the AAA games.
Sure.
But the trade-off is completely worth it because by pseudo-labeling this massive internet corpus, they inject real-world lighting, natural camera dynamics, and just crucial domain generalization into the training set.
Stuff that synthetic data engines just cannot replicate no matter how hard you try.
Exactly.
So the internet pipeline is clever, but the collection mechanism for the game and sim data is what really blew my mind. They didn't just write a script to scrape games.
No, they built an autonomous agent.
World Explorer.
Yeah, World Explorer. This thing operates 247 inside the game engines.
And sometimes it's running procedurally generated paths. Right.
Yeah, and other times it actually plays back real-world trajectories imported from physical devices.
Oh, to mimic human handheld jitter.
Exactly. And this agent operates completely unsupervised. But what makes World Explorer revolutionary is the training feedback-driven closed loop.
Right, because they elevated data collection from a dumb batch process to an active servo system.
Yes. Normally, the pipeline is entirely linear. You collect a petabyte of data, you train the model, you evaluate it, and you just kind of hope for the best.
Right. And if it fails, you have to start all over again.
Exactly. But in this system, the model's training performance is continuously tracked while the agent is collecting the data.
They built a weakness diagnosis module.
Yeah, it dynamically adjusts the agent's behavior on the fly. It basically acts as an automated curriculum at the data generation level.
So give us an example of how that works in practice.
Okay, so let's say the diagnosis component realizes the model is failing on long-tail scenarios, like generating coherent frames when the character is steering a vehicle at night in heavy rain.
It just turns into mush.
Right. So the system cross-references the performance metrics, updates the collection ratios, and actively pings the World Explorer agent.
And the agent responds.
Yeah, it dynamically shifts its task templates. It prioritizes spawning into nighttime, rainy environments to harvest more of that specific action state data.
So it's actively shaping the data distribution to target the model's blind spots in real time.
Exactly. All while maintaining a baseline collection floor across the other environments so it doesn't get catastrophic forgetting.
That is just brilliant engineering. And the rigor they apply to filtering all this data before it ever even touches the model is intense.
Oh yeah, 14 deterministic checks.
Across 6 dimensions, they're checking file integrity, detecting frame drops, enforcing geometric consistency so the camera isn't clipping through walls. But okay, my favorite detail is how they use vision language models for the menus.
Oh, to actively hunt down game menus. Yes.
Because that is a critical failure point.
Right. It is a massive problem when training interactive agents.
Because think about it from the model's perspective. Your agent is learning an action-to-pixel mapping, and suddenly the player hits the escape key and a giant static options menu pops up over the entire screen.
It totally ruins the training correlation.
Right. If you leave that in the data set, your model learns that pressing W to walk forward might occasionally just summon a giant UI window.
Yeah, it completely breaks the physics engine hallucination. The model just learns to ignore the user's actions.
Exactly. So by using VLMs to aggressively cut out cutscenes and UI pop-ups, they guarantee strict action conditioning integrity.
And by enforcing that unified filtering, they maximize the effective data ratio. But, this brings us to the core tension of the paper.
It's a drift.
Right. You can have the most perfectly action-labeled, weakness-optimized data set in the world. It literally does not matter if your architecture can't handle the compounding errors of autoregressive generation.
Yeah, autoregressive drift. I mean, if you've ever messed around with open source video generation models, you have seen this happen.
Oh, for sure.
The first 3 seconds look amazing. After 10 seconds, the background starts to warp. And by 30 seconds, the entire visual context just melts into a blurry soup.
Because in a closed-loop generation system, every prediction the model makes becomes the visual context for its next prediction.
Right.
So over a long rollout, these tiny estimation errors accumulate. And eventually, the generated history drifts so far away from the clean training distribution that the output just degenerates entirely.
So to tackle this, they used a causal diffusion transformer, a DIT, as the backbone. And they inject the raw keyboard actions directly into it using an action control adapter.
Yeah, this adapter takes the packed action tokens and uses a combination of pixel unshuffle, which reshapes spatial dimensions into channel dimensions, along with convolutions and raise blocks, to cleanly map the actions into the DIT's latent space.
Which is very slick. But the architecture feature that really solves a massive headache for them is how they handle third-person character identity.
Ah, the identity memory mechanism.
Yes.
It is a highly elegant solution to appearance consistency.
Yeah, I think of it as kind of a negative timeline. Like, let's build the problem first. If you're generating a 60-second rollout, by the time you reach frame 900, how does the model remember the specific details of the character's backpack from frame 1?
Right, because standard autoregressive models lose those details super fast.
Exactly. So here's the trick. Your current generated video tokens exist in positive time, frame 0, frame 1, frame 2. To anchor the visual identity, the model places reference character images in negative time, like time -3, -2, -1.
And by placing those reference tokens conceptually in the past, the causal video tokens in positive time can asymmetrically attend backward to them during the attention mechanism.
It perfectly preserves the third-person character identity.
It does. But because the attention is strictly causal and asymmetric, it doesn't break the autoregressive nature of the generation.
Right, the reference images just sit in the past, acting as an omnipresent anchor without needing, like, complex global conditioning networks.
It's so incredibly efficient. But, as you kind of alluded to, architecture tricks don't cure drift on their own. The training pipeline is where they actually solve the math.
Right, they don't just train a causal model from scratch.
No, they use a progressive bidirectional-to-causal pipeline.
Because bidirectional models learn global temporal coherence so much better.
Exactly. In a bidirectional model, every frame's attention can look at past frames and future frames simultaneously. It yields significantly higher quality visual dynamics.
So stage 1 is training this massive bidirectional teacher model on the multi-source corpus we just talked about.
Yep. Because it sees the full time horizon at once, it perfectly learns the physics and action condition dynamics of the world.
But a bidirectional model is totally useless for a real-time playable simulator.
Exactly.
I mean, you can't output frame 5 to the user's screen if the model needs to attend to frame 10, which hasn't even been generated yet.
Right.
You absolutely need a causal model that only looks backward.
Which leads to stage 2, converting that high-quality teacher into a deployable causal student. And they use teacher forcing and probability flow ODE distillation.
Wait, let me stop you there, because standard distillation usually just matches the student's step-by-step outputs to the teacher's outputs. How does probability flow ODE change that?
Okay, so instead of treating the generation as hundreds of tiny, noisy steps, probability flow ODE maps the diffusion process as a continuous, deterministic differential equation.
Okay.
This allows them to mathematically solve for the clean image trajectory. They freeze the causal context and train the student to jump directly to the endpoint of that ODE trajectory with very few denoising steps.
Oh, wow. So it preserves the visual quality and dynamics of the teacher, but it strips out the future dependence and heavily compresses the compute.
Exactly. But here's the critical bottleneck, and frankly, the reason previous models fail at infinite generation.
Exposure bias.
Yes. Local distillation is not enough. During training, the student is only exposed to short horizon, perfectly clean ground truth context.
Right, but in deployment, it has to condition on its own messy past generations.
And that mismatch between training context and deployment context is exactly what causes the drift.
Which brings us to the absolute centerpiece of this paper, LongForcing.
LongForcing, this is the secret sauce.
Yeah, break down the mechanics of LongForcing for us, because this is how they cured the hallucination soup.
So standard distillation aligns the student and teacher at the micro level, right? Single-step local transitions.
Yeah.
LongForcing radically changes the objective. It aligns the student and teacher at the macro distribution level over extended self-rollouts.
So during the LongForcing phase, they actually let the causal student unroll itself autoregressively for a long sequence.
Yep. The student generates frame after frame, accumulating those tiny errors and just naturally beginning to drift.
It's essentially forcing the model to look at its own mistakes.
Exactly that. Once the student has generated this messy, drifted rollout, they bring in the extended horizon bidirectional teacher to supervise that entire generated distribution.
Oh, that's wild.
Yeah, the teacher evaluates the drifted sequence and provides corrective gradients. It essentially tells the student, look, I see how you drifted away from the clean distribution here. This is the exact vector required to pull the distribution back to reality.
So it's providing corrective signals for long horizon context that short horizon training just completely ignores.
Precisely. And the empirical results are just staggering.
I saw the charts. When they evaluated this over 60-second rollouts, the LongForcing model maintained high HPS v3 scores, which, is a metric for human aesthetic preference.
Right.
And it kept patch repetition and color saturation artifacts near zero,
Huh.
while the baseline causal forcing model completely collapsed into static patches after just 30 seconds.
It mathematically proves that long horizon drift is fundamentally a distribution shift problem. And LongForcing actively regularizes that shift by teaching the model how to recover from its own compounding errors.
It's amazing. So, okay, LongForcing solves the math.
Yeah.
We have a causal model that will not hallucinate itself into oblivion.
Yes.
But solving the math in a lab does not mean it actually runs on a computer. If we try to push this mathematically perfect model through a standard 24 gigabyte RTX 5090, what happens?
Well, distilling the diffusion steps is nowhere near enough to hit 16 frames per second. The denoising budget is just one piece of the puzzle.
Right, because when you push for 720p interactive streaming at 16 FPS, the system bottlenecks violently shift.
You hit a complete brick wall with VAE decoding latency, transformer attention overhead, and KV cache memory traffic.
Which brings us to the deployment masterclass. Because to actually cram this simulated world into a 19 GB VRAM limit, they had to engineer a full-stack hardware-software co-design.
Yeah, let's start with the inference pipeline itself, Chunkwise streaming.
They don't generate the simulation frame by frame.
No, they generate 3 latent frames at a time, which magically decodes into 12 video frames.
Where does that ratio come from?
It comes from the temporal downsampling factor in their video autoencoder, which is set to a size of 4. So by jointly denoising a chunk of 3 latent frames in the diffusion space, they amortize the heavy attention mechanisms and decoding costs across the chunk.
So that massively boosts sustained throughput.
Exactly. You do accept a bounded, predictable control delay within that specific latent chunk, but the trade-off is achieving a much higher perceived frame rate for the end user.
But I had a massive question while reading this part of the stack.
Okay, what is it?
The DIT is obviously the heavy lifter computationally. It's doing all the complex physics, all the world generation. So why did the team spend so much engineering effort building Light VAE to aggressively prune the VAE decoder? Like, why not just use a standard off-the-shelf VAE to decode the latents?
It all comes down to that strict 1.2-second action to first frame latency budget. Yeah. At 1280 by 704 resolution, a standard VAE decoder is just far too heavy. Even if the DIT generates the latent chunk instantly, pushing those latents through a standard VAE to convert them into actual pixels takes too long.
I see.
And worse, it causes a massive spike in peak VRAM, which would immediately trigger an out-of-memory error on a 24 gig GPU.
The dreaded OV.
Exactly. So Light VAE strips down the decoder architecture to guarantee that the pixel conversion happens well within the latency budget while keeping the memory overhead completely negligible.
That makes perfect sense. You can't have the final pixel translation be the thing that crashes the entire GPU.
Right. And then inside the DIT itself, they implemented Sage Attention too.
Because attention computation is the dominant runtime cost when you're dealing with long token sequences at high resolutions.
Exactly. Sage Attention 2 replaces the conventional attention block. It fundamentally smooths out numerical outliers in the attention matrix and uses per-thread INT4 quantization under the hood during the calculation.
Wow, INT4.
Yeah, it dramatically reduces the per-step latency without requiring them to retrain the underlying architecture.
And paired with that is fast rope, which I thought was just such a clever optimization for this specific use case.
It really is.
Because if you are generating a continuous world, calculating the exact absolute position of every single token, say, out to frame 1500, requires intense memory bandwidth, and it becomes numerically unstable.
FastRope basically cheats this. It dynamically re-anchors the temporal rotary position embeddings locally.
Right, it tells the attention mechanism, hey, you don't need to know you are exactly at frame 1500, you just need to know you're 3 frames away from frame 1497.
Exactly. It saves a massive amount of compute and totally stabilizes the attention over infinite horizons.
But even with optimized attention, the real existential threat to infinite rollout on a single GPU is the KV cache.
Oh, absolutely.
I mean, if you keep caching the keys and values for every single frame you generate, just to maintain context, your memory footprint grows infinitely.
Yeah, you will run out of 24 GB VRAM in seconds, no matter how optimized your attention is.
So they implemented a bounded KV cache with rolling eviction.
Yep. They define a strict context window limit. Once the sequence reaches that limit, the oldest tokens are just evicted from the cache.
So the memory footprint of the KV cache becomes completely fixed.
Exactly. It takes up the exact same amount of VRAM whether you've been playing the simulation for 10 seconds or 10 hours.
But even a bounded cache for a 720p model is huge, which is why they go incredibly hard on low-bit mixed precision execution. This is where they really squeeze every drop of potential out of the RTX 5090.
They push the compute-intensive linear layers of the DIT backbone down to FP8, so 8-bit floating point precision.
Wow.
Yeah, FP8 serves as their default quality-oriented operating point. By dropping to 8-bit, it literally doubles the general matrix, multiply throughput, and halves the memory bandwidth requirements compared to standard FP16 execution.
But they can't quantize everything, right? I mean, if you crush the precision too much, the visuals have to degrade.
Precisely why mixed precision is necessary. While the heavy linear layers run in FP8, the numerically sensitive components, specifically the Light VAE and the text encoder, remain in higher precision.
Oh. So they preserve the visual fidelity and prompt alignment, but save the compute where it actually matters.
Yes.
And if you look closely at their system analysis table, they even pushed it further into MXFP4 and MXFP6 formats to find the absolute upper throughput limit of the hardware.
Yeah, they're really pushing the boundaries there.
But in their primary FP8 configuration, utilizing Sage Attention 2 and FastRope, the system hits exactly 19.281 GB of VRAM.
Which is just threading the needle at an unbelievable level.
Right. An RTX 5090 has 24 GB total, leaving roughly 4.7 GB for the operating system, background tasks, and display drivers. I mean, they are literally maxing out the hardware's physical potential without spilling over.
And the takeaway from their ablation study is stark. I mean, if they just applied Sage Attention 2 without also implementing Light VAE and dropping to FP8, the system immediately ooms. It just runs out of memory and crashes. Real-time deployment at this scale isn't about accelerating one specific operator. It requires this delicate, holistic balancing of transformer execution, video decoding latency, numerical precision, and runtime model residency all at once.
Bringing it all together, ABot-World-0 proves that building an interactive world model is a multidisciplinary engineering challenge. You cannot just scale a video model and expect it to act like a game engine.
No, it requires a completely full-stack approach.
Yeah. You need the active, weakness-targeting, closed-loop data collection of World Explorer to get the right actions.
You need the distribution-level rollout alignment of LongForcing to cure the autoregressive drift.
And you absolutely need the extreme inference co-design of Light VAE, Sage Attention 2, and mixed precision caching to actually run it on consumer hardware without melting the GPU.
And they proved this framework works by rigorously evaluating it on the World Roam Bench. They demonstrated highly competitive controllability and stable physical mechanics over extended rollouts.
They've successfully built a foundation for local visual simulators that can be continuously explored indefinitely.
It's an incredible achievement.
Which leaves you, the listener, with a pretty massive question to chew on. If a single desktop GPU can now simulate an infinite, physically plausible, and entirely controllable visual world in real time with accurate, ground truth actions, what happens to the future of robotics and reinforcement learning?
That is the big question.
Right. Will the next generation of embodied AI agents even need hard-coded game engines like Unity or Unreal? Or will they just be trained entirely inside personalized AI-generated simulators that can actively morph to expose the agent's weaknesses on the fly?
It shifts the entire bottleneck of physical AI.
It's no longer about painstakingly collecting real-world data. It's just about running better GPU simulations. Keep experimenting, and we'll see you on the next deep dive for AI Paper Slop.